Let's try the second approach. We will use doubly linked list to design. When we want to implement doubly linked list in my linked list, which is much faster, specifically, it will twice faster on the test case set here, although it will be a little more complicated. It contains the size, the sentinel head, and the third attribute is sentinel tail, and we should note that the sentinel head and the sentinel tail are always present, so all nodes in my linked list have a type of list node value plus 2 links, one link to the next and the other links to the previous element. So let's set a class my linked list, define double underscore initialize double underscore self, and then we set the size of the list is 0, which is default value, and then we set 2 sentinel nodes, self.head, which is pseudo head, self.tail, which is pseudo tail. All of them is list node 0 and list node 0, which is our default node, and then we connect self.head, the pseudo head, the next node, with the self.tail, which is the pseudo tail, and connect the self.tail.preview, the preview node, with the self.head. And after we define my linked list, we can trace back to define class list node. Let's define double underscore initialize double underscore self. It have x, and we set the self dot value is x, and we connect the next node self dot next, which is null, and self dot preview, which is also null. Its default value is null. Okay, so let's try to define add index. It have self and index, which is where we should insert. It is integer, and what kind of value we want to insert, it is also an integer, and we return null, means we will change the list itself. So first we should consider the edge case. If the index is longer than the length of the list, then it will not be inserted. We just return nothing. And another edge case is if index is a negative, means it's less than 0, then it will be inserted at the beginning of the list, which is assigned by 0. So first we just find the index we want to insert, and then we can find the 0, index -1, and self.size -1, and then according to these 4 indexes, we can divide our list into 2 parts, the left part and right part. The length of left part is index, and the length of the right part is self.size minus index. So when the left part is less than right part, so we just start from the left, because left part is more shorter and faster. First, we initialize our predecessor assigned by self.head, which is the beginning of the list, and then we iterate our predecessor assigned by predecessor.next, and this is inside our for loop for underscore in range index. So the time complexity is O of k time, while k is exactly the index. Then finally we get the predecessor, so we can update our successor, which is the predecessor.next, and then we just insert the index between the predecessor and successor. First, we can use our index to divide our list into 2 parts. The left part length is index, and the right part length is self.size minus index. So we compare the left part with right part. If left part is less than right part, then we just start from the left, which means it is shorter and quicker. And we first initialize the predecessor assigned by self.head, which means put it at the beginning. And then we use a for loop for underscore in range from 0 to index -1. And then we iterate the predecessor by assigning to the next node of the predecessor, and then After we finish the for loop, we get our last predecessor, then we can update our successor, which is the next node of our predecessor. First, we find the index we want to insert, and then we can find index -1 and 0, which is the beginning of the list, and self.size -1, which is the end of the list. And then, according to these 4 indices, we can divide our list into 2 parts. The left part length is index, and the right part length is self.size minus index. So we compare the left part with right part. Obviously, the left part is more longer, so we just search in the right part, which is shorter and faster. So let's begin at the end of the list. So first, we initialize our successor assigned by self.tail, which is put it at the end of the list, and then we update our successor assigned by successor.preview, and this is inside a for loop for underscore in range self.size minus index. So the time complexity is O of n minus k time, which is exactly as self.size minus index time. Then we finally get our successor, and according to this, we can get our predecessor, which is the previous node of the successor, and then we just insert the index between the predecessor and successor. So we should consider another situation, else, which means the left part is longer than the right part. So in this case, we should search in the right part because it is shorter. First, we initialize our successor assigned by self.tail, which is the end of the list. So let's start. First, we set a for loop for underscore in range from 0 to self.size minus index. So this is the length of our right part, which is more shorter and faster. And in each iteration, we update our successor assigned by the previous node of the successor. And then after finish the for loop, we just update our predecessor assigned by the successor.previous node. Let's say if we want to add an element as some index, the idea is simple. We just try to find the predecessor and its successor of the node to be inserted. So if the node to be inserted is at the head, its predecessor is our sentinel head. But if the node to be inserted is at the tail, its successor is our sentinel tail. So here, we're just using biconditional search to perform it faster. We insert the node just by changing the links to link the next node and the previous node. Let's say we want to add element 5, so it is our toAdd variable. We want to insert it between the predecessor and successor. So before we insert, we should notice the next node of the predecessor is successor, and the previous node of successor is predecessor. So first, we link the previous node of toAdd with predecessor, and then we link the next node of toAdd with successor, and then we link the next node of predecessor with toAdd. So this will unlink the next node of predecessor with successor, and finally, we link the previous node of successor with toAdd, and this will unlink the previous node of successor with predecessor. So first, let's declare variable toAdd and assign by the function list node, and the value is the val we just input, so it will create a new node and we assign to the toAdd, and then we start insertion. First, we link the toAdd dot previous node with predecessor, and then we link the toAdd's next node with successor, and then we link the predecessor's next node with toAdd, and then we link the previous node of successor with toAdd. So after we finish our insertion, we just update our self.size increment by 1 because we just add 1 element, so the length of the list will increment by 1. So let's try to define add at head. It has self and val for value as our integer input, and it output none. It didn't have the index because we just insert at the head. And first, we initialize the predecessor and successor. The predecessor is our first element, which is self.head, and the successor is our second element, which is self.head.next. And then we just repeat the speed, copy the code from here, Then we can define add tail. It has self and val for integer, and it also output none. So we initialize our successor and the predecessor. The successor is our last element, which is self dot tail, and the predecessor is our second last element, which is self dot tail dot preview node. So then we also repeat the same code here. So let's try to define another function, which is define delete at index. It has self, and index is an integer, is where we want to delete it, and then we return null because it will return nothing but change the node itself. First, we consider the edge case if the index is negative, or if the index is beyond or equal to the length of the list. Then we just return, and it will do nothing, it will not delete anything. And so we can, the other side, we can copy the code from here. But it is a difference between we want to insert and we want to delete. So the first difference is we want to change the successor. It will link to the next node of predecessor, and the same here. It will link to the predecessor will link to the previous node of successor, because the next node of the predecessor is what we want to delete it, and the previous node of successor is what we want to delete it. And after that, we should change the range, which is -1, because it not include the index. So after that, we should decrement the size, because we just delete one element, and then we just connect the next node of the predecessor with successor. So this will unlink the next node of predecessor with the middle element, and then we connect the previous node of successor with predecessor, and this will unlink the previous node of successor with the middle element. So these two unlink to make sure it be deleted. So let's try to define get. It has self and the index, which is an integer we want to get the value, and we output an integer, which is the value we want to get. So first, we should consider the edge case. If the index is less than 0, means negative, then it is invalid. Or the index is greater than or equal to self.size, that means it is beyond the boundary, then it is also invalid. Then we just return -1. And so let's start. First, we use the index to divide the list into two parts, left part and right part, and +1, because it should include the index itself. If it is less than self.size minus index, that means the left part is shorter and quicker. Then we will set a current pointer to start from the left part self.head, and we use a for loop to iterate them for underscore in range from 0 to index. So it is index +1, and every time we iterate our current, which is assigned by current.next node, and then another case is else. If it is if the index +1 is greater than self.size minus index, that means the left part is longer. Then we should start from the right, because the right part is shorter. Then we just initialize the current to self.tail, and then we set a for loop to iterate them for underscore in range from self.size minus index. So this will move the right pointer to the left, which is current is updated by the previous node of the current previous. So after that, we can get our latest current. Then we just return the current dot value.